10.6 talks about alternating series. So as it says here, we were only focusing on positive terms. Now we're going to start mixing in signs. So for example, looks like terms of the harmonic series, but we have some negatives kind of interspersed in here. It looks like we have plus, plus, minus, minus, plus, plus, minus, minus. So it's two positives, then two negatives, then two positives, and so on. So we have lots of ways that we can vary our sign patterns. And so that's kind of too much for us. What we're going to end up doing is just doing the simplest sign pattern we can, which is going to be alternating series. An alternating series means that these signs strictly alternate positive, negative, just one, 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 like that. So positive, negative, and so on. And remember that we achieve this by having -1 to some power in our terms here. So -1 to the k plus 1, think about what that means. Our first term, if we plug in k equals 1, we get 1 plus 1 is 2. So our first term should be positive. Right? And so if we have any even k, we would plug in here and get an odd power, and so we would end up with a negative. So all of the odd terms are positive, all the even terms are negative for this particular series. Our other option here is to have a -1 to the k. That means that all of our odd k's would be negative, all of our even k's would be positive. So we apply this to the alternating series and get what we call the alternating harmonic series. So we have the series -1 to the k plus 1. Again, that means that the first term is positive. So there we go. That's the alternating harmonic series. So without that -1 to the k, this guy here is just the harmonic series. It diverges. Right? We know that from previous instances here. So does adding alternating signs change the convergence or divergence of a series? We'll go ahead and take a look at this guy. So we have our n's here. We're going to go up to n. So we're going to sum up. We're going to take partial sums here. And as you can see, since we are adding and subtracting lower numbers at each time, it's going to sort of pull all of our values in toward this value where this blue dotted line is. And so we will get convergence with this guy. In fact, this guy does converge if you are interested. This is a particular case of what's called the Dirichlet eta function, and it will actually end up with natural log of 2 as the result. So this, sorry, not this one, the one that actually converges, this guy up here, the alternating one. And so we get natural log of 2. And so this guy diverges. This one converges to a fixed value there. So we see, does adding alternating signs change convergence? Yes, it certainly does. So now we want to investigate how so? In what way do we see that change? So in general, we're going to look at, for an alternating series, two different kind of parts of our term. We'll look at the alternating part, -1 to the k, and we'll also look at then sort of the rest of what makes our terms here. So what we're going to have here is alternating series are only going to look like one of these two things. We're either going to have -1 to the k, -1 to the k plus 1. The important thing is that alternating signs are provided by this particular bit, and it must be strictly alternating, which means it always must be, positive, negative, and so on, or negative, positive, and so on. So anything we talk about when we're talking about alternating series has to follow one of these patterns, and that's provided by this -1 to a power. So some other ways that this might be able to happen, we can think about what are some other ways that we can get -1 to a power every single time, either -1 or +1. We could think of maybe like cosine of pi times k. Right, if we think of that, if k is 1, then we get cosine of pi, which is -1. If we have k equals 2, cosine of 2 pi equals 1. So that's another option that we could have. When we end up with these guys, be very careful, because something like cosine of k is not alternating. Right? Cosine of 1 is something. Cosine of 2 is something else. It's going to be positive, negative, negative, Let's see, I think we switch over right about here. So this is not alternating. So we can only really have this alternating series if we are switching strictly back and forth between negative, positive, negative, positive. So here are the most common ways of doing it, the negative 1 to the k, or maybe a cosine to the pi k. As it says here, with the exception of the divergence test, none of the convergence tests for series with positive terms applies. So all the stuff that we've looked at up to this point, with the integral test, limit comparison test, root test, none of those work. So the fortunate news, as it says here, is that only one test needs to be used for alternating series, and it's pretty easy to use. So here's our alternating series test. So if we have a term or a series whose terms alternate signs, it will converge given these three things. So the a sub k's are positive. And you see also the a sub k's are non-increasing. So the a sub k's are separate from the negative 1 term that's bouncing things back and forth. So the a sub k's are separate from the alternator. All right, so you take everything except for the alternator and you examine that. Positive and non-increasing. We've seen this before in our integral test. So we're going to use the associated function. So we're going to make some function and show that it's positive and non-increasing. Right, remember non-increasing, it works if it is decreasing or constant. Either of those will work. And then lastly, the limit as k tends to infinity of the a sub k's equals 0. So as it says here, this is a little bit tricky. For a series of positive terms, the limit going to 0 does not imply convergence. Remember, the divergence test says that this has to happen for convergence, but other stuff has to happen too. But if the series is alternating and follows these two, then the limit does mean it converges. So since we are alternating terms and we're subtracting terms from one another, if the terms go to 0, that's going to be enough for us. So we just need to show these three things whenever we have an alternating series, and we'll know it converges. And so from that, we get a theorem here, alternating harmonic series. The alternating harmonic series converges even though the regular harmonic series diverges. So we'll go ahead and show that this happens using the alternating series test. So we go ahead and first separate the alternator from the rest of the term. So we have negative 1 to the n, 1 over n. And so now we have our associated function, our a sub k here is going to be 1 over n. So f of x will be 1 over x. All right, so we find our holes in our domain here. We have a hole at 0. And we sign test. We look on this side, and we test maybe 1. So f of 1 equals 1, which is greater than 0. So everything over here is positive. So a sub k is positive for all k. So we have, this is how we show our number 1 here. So number 2, we have to show that this is non-increasing. So we go ahead and look at the first derivative, negative 1 over x squared. And now we'll go ahead and find critical values and again sign test. So first order critical values where f prime of x does not exist. We have 0, but 0 was already not in our domain in the first place. So really we have none. So we'll go ahead and copy down our domain that we had before. I'll go ahead and put the hole at 0, which I really should have here anyway. And we'll go ahead and again test maybe x equals 1. So test f prime of 1 equals negative 1. So we get negative here. So a sub k's are non-increasing. In fact, they are decreasing, but non-increasing is all we need. And so the last thing that we need to check is we've got 1, we've got 2, we just need to show that the limit goes to 0. So we take the limit as n goes to infinity of 1 over n, and of course we get 0. And so we can say the series, we've got our series here, n equals 1 to infinity of negative 1 to the n over n, converges by alternating series test, AST. And so that would be our solution there. All right, so there's 3 components in the alternating series test. They are pretty short, considering what we have done with a lot of these other ones. So we can go ahead and keep using that. We'll go ahead and look at our next series here to determine whether the following series converges or diverges. Since we're doing multiple series, we say converge or diverge. This one is given as this sum, and we don't have the nth term, which means that we're going to have to kind of build it ourselves. So first off, if we're going to build a series, we see an alternation, positive, then negative, then positive, then negative. So we have some alternator going on. And we'll usually set n equal to 1 to start with. So we'll go ahead and keep that consistent here. Now we have to make sure this matches. First term should be positive, so let's go ahead and add 1 onto that. Next, we need to figure out how do we actually make this series. So we're looking at 2, 3 halves, 4 thirds, 5 fourths. Everything has a fraction here. Let's go ahead and put a 1 on that. Looks like a first term has denominator 1, second has denominator 2. It looks like all the denominators just match up with n. And then all the numerators seem to be just 1 more than the denominator, so n plus 1. And so this will be the representation in the series here of our series. So we'll go ahead and take a look at this, and I see that I have an n over n looking thing here. So I suspect, based on the divergence test, that this is actually not going to work. So we've seen something like this. If n is odd, and then if n is even. I'll go ahead and look at both of these. So we'll go ahead and set the limit as n tends to infinity of negative 1 to the n plus 1 over n. If n is odd, then we're looking at an even number up there. So we're looking at the limit as n tends to infinity of 1 times. So we just get n plus 1 over n. And at this point, we can just use L'Hopital's rule. Got infinity over infinity. Take L'Hopital's rule. We get 1 over 1. So we get 1. Technically, we should write the limit here as well. And on the other hand, if n is even, then if we take this same limit, and we just look at the even ends, then we'll get an odd power here. We get the limit as n tends to infinity of negative 1 times, and so we'll just go ahead and take it outside the fraction here. N plus 1 over n. Again, take L'Hopital's rule. And we'll have the limit as n tends to infinity of negative 1 over 1. And so we get negative 1. So not only is this not going to 0, we actually get that the limit doesn't exist. So therefore, we can just do the 3 dots. The limit as n tends to infinity of negative 1 to the n plus 1 times n plus 1 over n does not exist. And so the series diverges by divergence test, because our limit was not 0, certainly. All right, so we want to make sure that every time we look at a series, we always do that mental check first. So on this guy, we know that just by growth rates, natural log does grow slower than our polynomials, which means that this guy does go to 0, right? And if we are using alternating series test, we will have to find this limit in just a sec. But first off, we'll go ahead and separate then the alternator. We know for certain then that we do need to use alternating series test just because we've checked mentally that the divergence test is good. So here is our non-alternating part. So our function, our associated function, is f of x equals natural log of x over x. All right, so we got a couple things to check here. Where the natural log of x is equal to 0, or x is equal to 0. Right, if we want to do a sign test on this guy, we have to have our critical points. So where the top is equal to 0 and where the bottom is equal to 0. So we have, let's see, natural log of x is equal to 0 when x is equal to 1. And so here's what our domain is going to look like. We're starting at k equals 2, so all we really need to care about is 2 and onward. So we'll go ahead and plug in f of 2. That's natural log of 2 over 2, which is certainly going to be greater than 0. So a sub k is positive. And I'm just going to say we know that we're talking about for all k, so we'll only have to say a sub k is positive. So that's our first step. Second step, remember, is looking at the first derivative. So we've got low d high less high d low with the low squared below. So 1 minus natural log of x over x squared. So that's going to be our derivative. So we'll go ahead and find then our critical values here and do some sign testing. So we start with first order critical values where f prime does not exist. And we can see that the only place that would happen is where the denominator is 0, which is actually not in our domain from our original function anyway, so we say none. And so instead we look for first order critical values where f prime of x is equal to 0. So we set 0 equal to, if the fraction is going to be 0, it's got to be from the numerator. So 1 minus natural log of x is equal to 0. So natural log of x is equal to 1. And so the place where that happens is when x is equal to e. And we can just turn this into an exponential. E to the first is equal to x. So we'll go ahead and set up our number line then and sign test. Here's 0. Here's e. And so we need to check to the right of e, right? What's important is the tail of our series. So something that we could test is maybe e squared. That would probably be the easiest thing that we can do to determine our sign here. So we'll go ahead and look at f prime of e squared. That's 1 minus natural log of e squared over e to the fourth. So we get something positive in the bottom, and we get 1 minus 2. So we get negative over positive. That's something negative. So we get negative here. And so the a sub k's are non-increasing. And in fact, they are decreasing. And it starts at e, right? Our particular k starts before that. So, but e is, right, going to be slightly after 2. All that matters is that the tail is always decreasing, and that's what we got here. So the last thing we need then, we've gotten positive, we've gotten non-increasing. We just need to check now that the limit as k tends to infinity of our a sub k's here goes to 0. So we need to figure out then what exactly is going to happen here. We've got infinity over infinity. Let's go ahead and use L'Hopital's rule. When we do that, take the derivative of the numerator, we get 1 over k. And for the denominator, we get 1. The limit as k tends to infinity of 1 over k, well, we've seen that already. That's 0. So we've gotten all 3 components. Therefore, the series converges natural log of k over k converges by alternating series test. So I see all 3 components here. I can see the limit and I see my conclusion. Right. So on this next one, we see, just like I sort of mentioned earlier, there are other ways that we can get alternation. Kind of our prime other example here is cosine of n pi. Right. We look at the values of that. Again, we got cosine of, we start at 2 this time. Cosine of 2 pi, we get 1. Cosine of 3 pi, we get -1. Cosine of 4 pi, we get +1 again. So we can actually even say that this is equal to n equals, let's call it 2 to infinity. And we can say the first term starts out positive, so -1 to the n times 1 over root n. We can actually say that these are the same series. They have all the same terms, right? So that's what we got then. And so we'll go ahead and proceed with this. The associated function is going to be f of x equals 1 over root x. Right, so we do the same check as normal here. We go ahead and check for positivity. Critical values, we've got our domain has a hole at 0, and actually we can't get any negative values in it, so we'll just have the right side there. We'll plug in a test value of, say, 1. F of 1 is going to be 1 over root 1, which is 1. Since we're starting at 2, we really just need positivity past 2, but we get positivity over the entire thing for free here. Next, we go ahead and find f prime of x. Right, this guy is x to the -1/2. So we take the first derivative, we get -1 over 2, x to the -3/2. Right, that's -1 over 2 root x to the third. So that's going to be our first derivative there. And again, we check first order critical values where f prime does not exist. Well, that's where this guy is equal to 0, which we don't have at all. So then we check first order critical values where f prime of x is equal to 0. And we look at that, we've got -1 equals 0. That doesn't happen, so we get none there either. Again, if a fraction is going to be equal to 0, only the numerator can be 0. So we'll go ahead and have the same exact number line as for the original function. And we'll go ahead and test 1 is still an option, so we'll just use that. F prime of 1 is -1 over 2. So we have from here, I guess I didn't write my conclusions. The a sub k's are positive, a sub k's are non-increasing. And finally, we check the limit. The limit as n, I guess these are a sub n's, aren't they? A sub n, a sub n. Make sure our variables match. So the limit as n tends to infinity of 1 over n to the 1/2, which we know goes to 0 as well. Therefore, the series cosine of n pi over root n converges by alternating series test. So that's great and all, but we had all of these different convergence tests, and it's a shame that we can't use any of them here. It's a shame that we can't use something like the root test or even limit comparison, stuff like that. And so what we'll do is we'll say, what if we want to see, can this guy converge if I just took the alternating part out? If I just remove that alternating part completely, can the series still kind of survive that? How well does this series converge? And so we'll talk about that. We'll talk about different qualities of convergence now. Absolute and conditional convergence. If we take away the alternating signs, sometimes we'll end up with a convergent series, but sometimes we won't. So we'll use new terminology that distinguishes the cases. Are the a sub n's in this case kind of strong enough to converge even if the alternation is gone? We can see that this is a p series, so definitely not, because p is too small. We can see maybe in this case back up here, this will diverge in either case. Our harmonic series, if we take away the alternator, now it diverges again. There are some series, though, that even if they're not going to have that alternator, they'll still converge. So we'll go ahead and talk about those as different series now. So the infinite series converges absolutely if the corresponding series of absolute values converges. So we put absolute values on it. That gets rid of our alternator. And if it still converges, we'll say it converges absolutely. A series that converges but not absolutely converges conditionally, or is conditionally convergent. So if a series needs that alternator to converge, we'll call it conditionally convergent. If a series doesn't need it, we'll call it absolutely convergent. So a series like this, we have -1 as our alternator there, and we have it over k squared. If I apply absolute values, it gets rid of that -1. It gets rid of that alternator, and we're just left with 1 over k squared. That's a convergent p-series. So removing the alternating signs does not affect the convergence, which means that this guy is absolutely convergent. So that's kind of our highest example now that we can get of convergence. We now have a higher standard of convergence, a lower standard of convergence, and a divergence. So we'll have to find which one is which. So something like the alternating harmonic series, if we apply our absolute value, gets rid of the alternator, we have the harmonic series that does not converge. So this guy converges, the alternating harmonic series does converge, but it converges conditionally. A convergent series may not converge absolutely, but if it converges at all, it's conditionally convergent. If a series does converge absolutely, it converges no matter what. So if an absolute value causes things to still converge, if it converged without the alternator, then it certainly will converge with the alternator. That's what this theorem says. If it converges without the alternator, then it will certainly converge with the alternator. That being said, if it diverges without the alternator, then it will certainly diverge with the alternator. Sorry, other way around. If it diverges with the alternator, then it will diverge without the alternator. Let me go ahead and state that. If converges without alternator, then it converges with. If it diverges with the alternator, then it will certainly diverge without. So if even the alternator is not enough to make our series converge, then certainly taking the alternator away will definitely make it diverge. So this is what we'll start to do. It says determine whether the series diverge, converge absolutely, or converge conditionally. We have now 3 things to check for, and so we're going to want to start with the strongest thing that we can. So what we're going to do from this point on is whenever we are looking at a series that we want to check for convergence, we're going to first apply absolute values. So we'll take this guy, we'll apply an absolute value to it. And in this case, there is no alternator, so it's just the original series again. So we know if this guy converges, it should converge absolutely because we did apply absolute values. And this is a convergent p-series. So a convergent p-series, what is the value of p? It's equal to 3. The series, therefore, converges absolutely. So with the absolute values on, it still converges. So it converges absolutely. All right, so what about this example? Again, first step we do is we apply an absolute value. So we apply our absolute value, it gets rid of our alternator. So k equals 1, to infinity of 1 over root k. That's going to be the same as 1 over k to the 1/2. That's another p series, but in this case, p is 1/2. So this is a divergent p series with p equal to 1/2. What that tells us is the series does not converge absolutely. So it does not converge absolutely. But that means we still have two other options. Does it converge conditionally? Does it diverge? We have to figure that out. So to figure out if it converges conditionally, we go back here and look at the same series again. This time we do not get rid of the alternator. We instead use alternating series test. So we'll go ahead and use AST. We did this 2 examples ago. Doesn't make sense to write down the same work. And we find that it does converge. So after we take off the absolute values, it does converge. So therefore, the series converges conditionally by alternating series test. This is the only way that we'll really find that something converges conditionally. If you ever write a series converges conditionally, it'll always be by alternating series test. Because if it converged by something else, then we were able to use it when those tests only work when the terms are positive. So we would have had to have either absolute values or a positive series to begin with. In either case, if we find convergence, then we'll have an absolutely convergent series. If something diverges back when you apply the absolute values, and it also diverges under the alternating series test, then we'll actually say that the series diverges. All right, so we'll continue on here. Determine whether the series diverge, converge absolutely, or converge conditionally. So again, we're checking all three. We'll go ahead and first apply absolute values then, if we're supposed to check for all three. So we go ahead and apply the absolute values. That gets rid of the alternator. So we get 1 over the square root of k cubed. That's going to be equal to 1 over, instead of the square root there, we'll change that into a rational power there. And this is a p series. P is 3/2. So this is a convergent p series. With p equal to 3/2. And so we applied the absolute values here and we got that it still converges, which means that this series converges absolutely. And I can see on the previous line why. A convergent p series with p equal to 3/2. All right, so we'll look at the next one here. So here's a problem. Since we have sine of k, remember that this is not going to be strictly alternating. Sine of 1 is positive. Sine of 2 is also positive. Sine of 3, that's just under pi, so we're positive. Sine of 4, that's over pi now, so we're negative. Sine of 5 is negative. Sine of 6 is negative. That's just under 2 pi. So sine of 7 will be positive again, and so on and so forth. So this is not strictly alternating. So not strictly alternating. So AST cannot be used. The alternating series test cannot be used because this is not alternating. The signs are changing, but not well enough, not consistently enough for alternating series test, which means that when we apply our absolute values, we better hope that we get a convergence here. So we better hope that this is absolutely convergent. One thing that we know is that k squared is always positive, which means the absolute values don't really matter for it. So we can actually just apply the absolute values to the sign instead. So we'll have to go ahead and figure out how can we get this somehow through our tests. Since sine of k with absolute values on it is always positive and k squared is always positive, this is a positive term. Whenever we apply our absolute values, we end up with positive terms, which means that these are fair game for any of our other tests. So the usual problem with sine is that it kind of bounces back and forth. So what we want is we want to maybe compare this to something a bit more stable. So we'll use comparison test. So we know that the sine of k has to bounce in between -1 and 1 for all natural numbers k. So for all k in n, the natural numbers. So we'll go ahead and figure out division here. So dividing by k squared will not change the direction of inequality. Because k squared is positive for all natural numbers k. So we obtain -1 over k squared less than or equal to sine of k over k squared less than or equal to 1 over k squared. And then we apply the absolute values. When we do that, we get the absolute value of the sine of k over k squared is less than or equal to 1 over k squared. Absolute values aren't going to matter here. Right? And 1 over k squared is a convergent p-series. With p equal to 2. And since our series has terms that are less than or equal to 1 over k squared, our series in total here, sine of k over k squared, converges absolutely by the direct comparison test. So we're able to show that applying the absolute values, we're able to get that our terms are less than that of a series that's known to converge, which means by direct comparison test, we know this guy converges. So we have now a roadmap for how this should work. We'll go ahead and keep going with this. We apply the absolute value. When we do that, our alternator goes away, if we have one here. If it's not an alternator, if it doesn't just bounce back and forth between -1 and 1, we do have to keep it around. But since this bounces back and forth between -1 and 1, the absolute value of that should just be 1. So we just get k over k plus 1. Hey, wait a minute. We're looking at this. I didn't really check to see if our divergence test works yet. So looking at this, we can see right now, so you can catch it at this point, that if we were to take the limit here, that this would go to 1. The thing is, if we applied divergence test here and look at the limit as k tends to infinity of this guy, we use L'Hopital's rule, and we get 1. We know that this guy doesn't converge, but that means that we could go back and see if we remove the absolute values and we just look at our original series, maybe it converges conditionally. So that's why you always want to do divergence test first. So important note, if you were wondering why we back up here had to look at both the odd and the even, if I go all the way back here, odd and the even ends, this is a similar series. The reason that we had to do that is because if we go ahead and apply absolute values, and we find the same thing, that it doesn't go to 0, we still have to go back and check to see what if the alternator changes it. So always do divergence test first and foremost, even before you necessarily apply your absolute values. So we'll go ahead and look at that, and it should be very similar to the other one. So if k is odd, the limit as k tends to infinity of our series terms here, we get the odd, so we get negative on that, negative k over k plus 1. Take L'Hopital's rule, we get the limit as k tends to infinity, negative 1 over 1, and so we get negative 1. If k is even, then our limit here, we would get an even power on that negative 1, and so we would get positives. So we just get k over k plus 1. Again, applying L'Hopital's rule. So we get the limit as k tends to infinity of 1 over 1, which is 1. So we get that thus the limit as k tends to infinity of negative 1 to the k times k over k plus 1 does not exist. And therefore, the series diverges by divergence test. So again, divergence test is the very, very first thing that happens, even if you are looking for all three of these things. Because if you go ahead and apply the absolute value, find that it diverges, you're going to have to take the absolute value off and do it again. So it's a lot better just to apply divergence test first, that we can catch that kind of thing. So we apply divergence test. If we find that the limit goes to 0, we'll go ahead and apply our absolute values, and then we'll run it through trying to find whether it converges under the absolute values. If it doesn't, we take the absolute values off and try it again using alternating series test. So here is, with all of this stuff, the sum up when testing a series for convergence. First and foremost, divergence test. Apply absolute values, move on to the next step. Right? If back here we have divergence, then there's no point in doing any of the other stuff. It diverges. Apply the absolute values, move on to the next step. If the series converges at that point, it does so absolutely. If it does not, you have to test for conditional. So we have absolute values on. Then we go through all of our basic convergence stuff. So including, root, comparison, integral, all that kind of stuff. If all of these guys here, if any of them show divergence, then we'll do the alternating series test. Take off the absolute values, do alternating series test. If it converges, it does so conditionally. If it diverges, then the series diverges. So that's the full list of all of the tests that we have up to this point. So that's the full list. Let's go ahead and look at this handy table at the very back of our section here, and you can feel free to, if the if the table is showing up strangely on eCampus, go ahead and try downloading the Word file, and I think there's an extra line that sometimes gets added on. Go ahead and delete that. So we have here a pretty good sort of sum up of all of our different tests. We've got divergence test. Remember, there's no way to find convergence by the divergence test, otherwise it'd be the convergence test. We have geometric series. One important thing that's missing is the telescoping series. You have to remember, just use sequences of partial sums. We have the integral test. We have all of the different requirements for it. Right? P-series, ratio test, root test, all the comparison test, and now alternating series test. So this is a good sum up for all of that stuff. So that's going to be the end of our chapter 10. Series will return in the next unit, and we'll go ahead and look at some more interesting variations on series. But that's going to round it off for this unit.